My name is David Van Vranken, and I want to welcome everybody to the 18th lecture in Chemistry 51C Organic Chemistry here at UC Irvine. We've been talking about enolate chemistry, which is super exciting, and I wanted to take a moment to talk about molasses, which doesn't seem very chemical, maybe. This weekend, I was baking some French toast sticks with my daughter, and we ran into an emergency situation where we didn't have enough maple syrup. And so I thought, well, why don't we try some molasses on there? It's sweet, it's syrupy. And so I pulled out the bottle of molasses and, you drizzle some of that stuff on there. And I noticed on the bottle that it said unsulfured molasses. And that makes it interesting. Once they talk about sulfured or unsulfured, there's clearly some chemistry going on. And the thing that kind of struck me initially was the fact that here's this bottle of what is presumably a deep south kind of ingredient, Louisiana, Mississippi, that kind of stuff. And they're using a United Kingdom spelling. You know, in the United Kingdom, they spell sulfur with a PH. In England, in the UK, in the United States, we spell it with an F. So it's odd to me that they're using a UK spelling, but they're not using the United Kingdom name treacle they're using, it just seems like this, just a weird juxtaposition of terms here. But what's going on with this sulfurization? If we want to understand the sulfurization, the sulfured, unsulfured, well, we really need to understand where molasses comes from. It's a product of sugarcane refining, and it's very chemical for me as a synthetic organic chemist. So I found this cool diagram that was drawn by Sean Gaskin. And so when they harvest sugarcane, they take all the sugarcane, sometimes they burn off the leaves in the field. They put them into this cane crusher, which then rolls out the juice from these sugarcane stalks. And then they take the juice and they mix it with lime, which is calcium oxide or calcium hydroxide when it mixes with water. They're just using that as a base. Calcium hydroxide is a base. The cane juice is kind of acidic. And it's at several points in this process that they can blow in sulfur dioxide gas. And why would they blow sulfur dioxide gas in there? When you treat sulfur dioxide gas with water, there's some chemistry that happens. I'll talk about that in a second. So here's one place that they can introduce sulfur dioxide, and usually they generate that on site. They burn sulfur. It generates sulfur dioxide. That's what you're smelling when you strike an old-fashioned match, and you can smell the sulfur dioxide coming off of there. The other place that they can add sulfur dioxide is down here. So once the cane juice gets treated with base, this calcium hydroxide base, then gets heated up, and they filter off all these insoluble particles, and then they evaporate a lot of the water from the cane juice to really concentrate down those sugars. And so after the evaporation is another stage that some sugarcane mills choose to introduce sulfur dioxide. And then they evaporate it even further in what's called these vacuum pans. And it's at this point where the solution is super saturated, and that's when you expect crystals to start forming. Synthetic organic chemists grow crystals all the time in the lab as a method of purification. And we usually filter the crystals using a filter paper or a vacuum filter funnel called a Buchner funnel. They use a centrifuge in this process, which spins out the goopy liquid that's left over. We refer to that as the mother liquor. So when you do a crystallization, there's the goopy gunk, the liquid, that's the mother liquor. We throw that out, and then the crystals are the pure organic compound. I love the fact that when I eat sucrose, I'm eating a pure crystalline organic compound. But even though we normally throw out the mother liquor in a synthetic organic chemistry lab, that's what they're selling as molasses. It's that mother liquor that's left over after the crystallization. It's cool to me that I'm putting mother liquor onto my French toast sticks or on cornbread. I put molasses on cornbread because I'm from Texas. And then the sugar crystals that they get are usually not completely pure. They put those through a second recrystallization to get them to be white. Okay, what's this sulfur dioxide for? Let's talk about this chemistry of sulfurization. This is the chemical structure of sulfur dioxide over here. Um, and in the presence of hydroxide, like calcium hydroxide, because of the lime they introduce, that reacts with hydroxide or water to generate. Um, there's two different resonance structures I can draw here, but I would refer to this as bisulfite. I don't know if I can write the name here. This species is called bisulfite. And here's another resonance structure that's very unusual for bisulfite. I'm drawing this resonance structure on the bottom to emphasize the fact that the sulfur is nucleophilic, right? There's a weird resonance structure I can draw with S minus, and the lone pairs on that sulfur can attack aldehydes, especially aldehydes attached to colored compounds in the sugarcane juice. And so once they add in to that aldehyde, it forms a sulfur carbon bond. And at pH 7 or close to neutral pH, that exists as the sulfonate anion. And that means it's water soluble and can be easily washed away from the crystals at the end. And likewise, any enones that they have over here, any enones that they have that are attached to colored chromophores in that cane juice, sugar cane juice, is also susceptible attack through a conjugate addition reaction, just like a cuprate, and just like a reaction we're going to see in chapter 24 coming up, called a Michael addition, where the sulfur lone pairs on that bisulfite anion can add into the enone, just like a cuprate, and generate this enolate, which is rapidly protonated in solution. So I guess I didn't really draw that, but in solution, you've got either some proton species that can push down here, pick up the proton, and so you end up with, you pick up a proton on the enolate, and you lose a proton from here. I'm not showing all the steps, and generate a water-soluble compound. So both of these compounds here are water-soluble, and so they can use that to wash out the colored components and end up with lighter colored sugar crystals. And I guess they don't do this if they're making that brand of molasses. They sell you molasses that has not been treated with stinky sulfur compounds. And that's kind of cool. I'm not sure if this is the right word, sulfitation, I wasn't sure how to spell that. So today we're going to finish up the chapter 23 in the Gorzynski-Smith textbook in the 5th edition that talks about making enolates and using them for SN2 reactions. And then we're going to start on chapter 24 because we only have a couple of things left to talk about. And chapter 24 is also about enolates. But instead of using enolates for SN2 reactions, in chapter 24, we're going to use the enolates as nucleophiles to attack carbonyls. So that's the main things we're working on today. So you may recall when we left off on Monday that we talked about how LDA is very selective. And so here's an example of a substrate that can be deprotonated on either side, but LDA is choosy. It's got isopropyl groups that are sterically encumbering that makes it attack very selectively on the less hindered side if both sides are about an equal acidity. And then you can treat that with nucleophiles for doing SN2 reactions. Methyl iodide, allyl bromide, benzyl bromide, alkyl tosylates. You just want things that don't lead to a lot of E2 elimination competing. Now, what happens if you want to alkylate and make the enolate over here on the other side of the molecule? LDA doesn't do that. And the book shows you a trick. And it's not super reliable, but it's the only trick we're going to give you. And that is that if you use a weak base, not a strong, powerful base like lithium diisopropylamide, but a weak compared to LDA. T-butoxide, potassium T-butoxide is a classical base where it's not powerful enough to make a high yield of the enolate. But what it can do for you is it allows you to make a tiny amount of enolate. Let me try to switch to my black pen here. It allows you to make a tiny amount of the enolate. And it prefers to make the more stable enolate. There's a little bit of the enolate on the other side, the side that's not on the methyl group, but the main enolate that's present there is the more stable enolate. There's not a lot of it. Let me just write that down so we're clear. I'm not saying there's a lot of the enolate. There's just a small amount of this present in solution. And this is an equilibrium process. It's going back and forth And most of this will exist as the starting material. So you've got mostly ketone just sitting there, and then a tiny amount of the enolate, and the dominant enolate is the one that's more substituted, where you deprotonated on the more substituted side. And if you do these in the presence, let me put a bracket around here just to be clear that this is a synthetic intermediate. You're not synthesizing this and isolating it. There's just a small amount of that in solution. If you do this in the presence of methyl iodide, so it has to be present in the reaction mixture, all mixed together at once, then you can get the enolate to attack. And let me go ahead and draw up that arrow pushing there. You can get that enolate to attack and form a carbon-carbon bond on the more substituted side. There we go. And let me draw that bond and break that bond. And so you can't do that with LDA, because LDA selectively deprotonates on the less hindered side when both sides of the carbonyl of the ketone are comparably. And so that would put a methyl group on that. So, okay, so potassium T-butoxide in the presence of your alkylating agent. And notice how I've used an alkylating agent that can't undergo E2 elimination, right? If you put in something that's capable of E2, you're probably just going to destroy a lot of your alkyl iodide through E2, but there's no beta protons on methyl iodide. And so that's why that works. Okay, let's go ahead and walk back historically, maybe 60 years or something. You know, LDA was only developed, I think, maybe around 1970. What did people do before that? People still used enolates, but you know, without LDA, you had to be very careful and clever about how you did enolate chemistry. And here's the trick. I wish I'd drawn a different, let me try to draw more of this. I wonder if I can draw with a white thing here to cover up that ethyl group here. I'm going to try to draw out the ethyl group on one side, just because I want to make it clear what's important about this reaction. Now there's hydrogen atoms all over this substrate here, but those aren't acidic. Here, those aren't acidic. But the protons that are between two carbonyl groups are super acidic. They're more acidic than water. And that means we can use bases like sodium ethoxide, which can't make a regular high yields of a regular enolate from a ketone or an ester or an amide. But when there's two carbonyls, it's so acidic that we can use a weak alkoxide base. And this is what we did before the development of LDA around 1970s. We used one 3-dicarbonyls that had CHs in between the two carbonyls. And so when we do this, we're going to generate this super stabilized enolate. This time I'm just going to draw ET here because we don't really care, right? It's only those protons that are between the two carbonyls that are acidic enough. Now there's a couple of different resonance structures I could use here. I'm going to draw, I can't resist drawing the arrow pushing because I love thinking about those mechanisms. I'll draw the resonance structure where I leave the electrons on carbon, but you could push the electrons all the way into the carbonyl if you wanted. It really means the same thing. I don't have to draw this H, but I'll draw that there. And that leaves a carbanion. And you can use that carbanion for doing SN2 reactions. So we treat with sodium ethoxide, then we'll treat with some reagent for doing SN2. Let me use the methyl iodide again. That's super common, CH3I. There's a bond there. And then this will do an SN2 reaction. There we go. And you don't need to write sodium ethoxide THF minus 78. It's just sodium ethoxide. Usually they use ethanol as the solvent, but it's not really important. And so here's the product of our reaction. We've not made a new carbon-carbon bond. And so as long as you're not annoyed by the fact that you have to have two carbonyls on there, you can do enolate chemistry using alkoxide bases. And that's the product. I'm not going to draw the H or the lengthen this carbon-carbon bond. That's the product of the reaction. All right, this ester here that I started with is an ester of malonic acid. Let me go ahead and draw malonic acid. This is malonic acid. And that should be an O in there. And this ethyl ester is diethyl malonate. Okay, why are we teaching you this stuff that's from the 1950s and the 1960s? Why don't we just teach you the LDA chemistry? Well, this is the way the human body makes carbon-carbon bonds, is using malonic acid derivatives. Inside of all of your cells have biochemical pathways for generating all the carbon-carbon bonds in fatty acids. And those are generated using this malonic ester anion. You make an enolate and it attacks another molecule and makes a carbon-carbon bond. So these types of stabilized enolates that have two carbonyl groups on there are super important in biochemistry on organisms in the planet Earth. Okay, here's, we don't always want two carbonyl groups on our molecules. And it turns out there's a secret trick we have to get rid of one of the carbonyl groups. So let's just remind ourselves of our root here. What I told you is that if you have some sort of an ester, it could be a methyl ester or an ethyl ester, as I'm showing here. I think diethyl malonate is the inexpensive one, or it's the one that's most commonly used. And what I told you is you could use sodium ethoxide, I'll make that small Roman numeral, to make the enolate. And then step 2 would be some sort of an alkylating agent. Here we're adding methyl, so let's make it methyl iodide to make that carbon-carbon bond. Now, what happens if we don't want one of these carbonyl groups? Well, it turns out we can get rid of them. You just treat your ethyl ester, your malonic ester, with hydrochloric acid in water and heat. And those are standard conditions for hydrolyzing esters. You could take methyl esters and hydrolyze it. It doesn't matter whether there's one ester or two, whether it's attached to a benzene ring. These are very general conditions for hydrolyzing esters. So what's really happening in this reaction is it's not just that you're hydrolyzing both of the esters, but you'll notice that one of the carbonyl groups is gone. And so let's go ahead and draw out this important intermediate. There's a 6-step mechanism that's the opposite of Fischer esterification that hydrolyzes these both of the esters. And it turns out that in the presence of heat and acid, whenever you have a carboxylic acid next door to another carbonyl group, it turns out that it decarboxylates. It loses carbon dioxide, so minus CO2. Here's the, I'm not sure if I didn't do a good job of writing that minus symbol, so let me try to use a little white pen here to erase that. Whoops, that's not a white pen color. Let me try to erase that with a white pen. So that's minus CO2, that's what you're losing there in the reaction. What you're looking for this decarboxylation, and this is spontaneous. Anytime you have some sort of a carbonyl group, and I'm going to rotate the bonds here, it's the same molecule, they can adopt this conformation. These are unstable in the presence of heat and acid. And they're unstable because they do the following reaction. They do this transformation where you lose carbon dioxide. If you follow my arrows, I'm going to push my arrows here. And you end up with an enol that rapidly tautomerizes. It doesn't matter how you generate this carboxylic acid with a carbonyl group at the beta position. Doesn't matter whether it came through hydrolysis. If you take any carboxylic acid that has a keto group, a carbonyl group, 2 atoms away from the carboxylic acid, you'll get this decarboxylation when you heat an acid. So that's how they used to do enolate chemistry. And this is the way the human body does enolate chemistry, is you make the stabilized enolate, then you do SN2 reactions to make the carbon-carbon bond, and then you hydrolyze and decarboxylate. And both sides were identical here, so it doesn't matter which side lost the carbon dioxide. And then once you lose one of one of the sides, you can't lose the other. And so you end up with a carboxylic acid as a product at the end of the reaction. Okay, right, this process is pretty general for 1,3-dicarbonyls. If I draw some enumeration around this, I would refer to this as a 1,3-dicarbonyl. You could also refer to this as a beta-ketoester. So, right, remember our nomenclature. If this is the ester here, would be the alpha carbon, and this would be the beta carbon. So this would be referred to as a beta-ketoester. And it's just like the malonic ester idea, that we can take this this beta-ketoester and treat it with an alkoxide base and generate a high yield of the enolate. So I'm not sure I really need to draw the enolate here, but once you generate the enolate at this position with the sodium ethoxide, you can do SN2 reactions. And so the product of this process that I've drawn for you here would have a new carbon-carbon bond. So if you started off with an ethyl group here, and then you add a methyl group, now we have a quaternary center, and there's no H's left to substitute. So you can, if you start with two H's in between the two carbonyls, you can replace them one at a time using this two-step process of deprotonate with alkoxide base, and then add methyl iodide. Could you use LDA in this process? I think in theory you could. Yes, you could. But nobody would do that because you have to make LDA in the lab. If you want to do a deprotonation with LDA, you come in the morning, and the first thing is you spend the morning making a solution of LDA. Whereas sodium ethoxide, you scoop out of a little canister. No human being on the planet would bother to make LDA for this deprotonation when you could just scoop some stuff and weigh it out on the balance, and your reaction is going. And again, this idea of ester hydrolysis and decarboxylation applies here even when there's a ketone on the other side. So let's just refresh our memory here. What's the conditions? So to hydrolyze the ester here to a carboxylic acid, you can use HCl and then in water, and we're going to heat it. Usually 100 degrees, 24 hours. And then the carboxylic acid spontaneously loses carbon dioxide. You can't stop that from happening. And you need to recognize this pattern, right? This pattern that's, there's another byproduct here that results from the ester hydrolysis. I'll go ahead and draw the intermediate that you get here, although it's not really that interesting to draw. So just remember the conditions are mainly to hydrolyze the ester to make this compound that is unstable, and you get ethanol as a byproduct in this reaction, but that's not the interesting part. And then that loses CO2 because I told you it will, whether you want to or not, if you're heating an acid, that will spontaneously decarboxylate. Okay, this process of the malonic esters, the acetoacetic ester synthesis, where there's an acetyl group on this side and an ester on the other side, it allows you to create a substitution pattern that you cannot generate with LDA. So if I tried to take this type of a ketone down below and treat it with LDA, and then put the methyl group there, or the other way around, if I had the methyl group on, I tried to put the ethyl group, LDA cannot deprotonate on that side. That's the more substituted side. LDA deprotonates the less substituted side. So you can't make a molecule like this using LDA. Here's what you get. Let me draw this in black pen. The initial deprotonation event with LDA doesn't occur on the side that has the ethyl group. The initial deprotonation event is going to occur over here. And so now, I guess I didn't have to draw those brackets, but now when we treat this with methyl iodide to do the SN2, that methyl group ends up over here. And so that's not the same product that we made up above here. It's a different substitution pattern. So, this whole acetoacetic ester thing is far more clunky in terms of how many steps you have to remember. You have to sodium ethoxide, methyl iodide, and then follow it up with this HCl and water. But it does allow you in this particular instance to get to a substitution pattern for ketone substitution patterns that you can't get to using LDA. All right, that's all we have for our chapter. What did we just do? Let's go ahead and get ready to start on chapter 24. And in order to help us get ready, I want to give you this roadmap for what we're doing in this course. It's based on the Gorzynski-Smith textbook, the 5th edition. Go ahead and change this to single page view. The Gorzynski-Smith, the 5th edition of Gorzynski-Smith. And we've already had an exam, 2 exams. The first exam covered chapters 18 and 19 in the Gorzynski-Smith textbook, which was electrophilic aromatic substitution, and then phenols and carboxylic acids and their acidity. And then we just had another exam on carbonyl chemistry, addition of Grignard reagents, hydrido reagents to carbonyls, to esters, to ketones, to amides. And then we had two other chapters on carbonyl chemistry. The first one was really specific to ketones and aldehydes, so making imines, enamines, cyanohydrins, acetals, and then they threw the Wittig reaction in there because it didn't seem to fit anywhere else. Don't forget the Wittig reaction. And chapter 22 was all about carboxylic acid derivatives, acid chlorides, esters, amides, making amides, hydrolyzing esters. And then they also had nitrile chemistry in there as well. You can hydrolyze nitriles to carboxylic acids. And so we just finished a chapter on enolates, making enolates and then using them for SN2 reactions. And thrown in there was this weird reaction where you can brominate alpha to a carbonyl group using Br2 and acetic acid. So now we're getting ready in chapter 24 to take enolates. We're going to make enolates, and then we're going to add those enolate nucleophiles to carbonyl groups instead of doing SN2 reactions. Let's go ahead and get started with chapter 24. It's enolate. Man, we're finally getting to the stuff that really is the heart of modern organic chemistry. So the canonical reaction for making an enolate and adding it to a carbonyl is called the Aldol reaction. The alds comes from the word aldehyde. So classically, it's a reaction of aldehydes and base. And let me show you what's happening. What is it that constitutes an Aldol reaction? So with an Aldol reaction, you're making enolates. So it may not be obvious to you here, but what's happening is you're making an enolate. And let me be a little bit more specific. That when you run reactions and you put substrate in your flask, you don't have just one molecule. You have like 6.02 times 10 to the 23rd molecules. So don't freak out that somebody might not draw that second copy of the molecule for you. I promise you there's more than one molecule in that flask. So when you take aldehydes and you treat them with base, you're going to start to form enolates, and those enolates will then add to carbonyl groups. That should not be that shouldn't be a big mystery, because we've spent this quarter learning that nucleophiles love to attack carbonyl groups. And there's a proton transfer event that's going on in there. Let's go ahead and draw the full mechanism out. I've got some space for that down below. If you wanted, you could use sodium methoxide. You could use sodium ethoxide. You could use potassium T-butoxide. If you wanted to go in the lab and make some LDA, I guess in theory you could, but we'll talk about that a little bit later. A classical aldol, you use an alkoxide or hydroxide base. Now, there's protons here that are next to the carbonyl group. And those protons are somewhat acidic. So they're acidic enough for you to generate a small amount. You know, it's not like all of it quantitative. I'll just draw an equilibrium here just to indicate there's a small amount of this enolate that gets formed when you deprotonate next to the carbonyl. So let's go ahead and draw that arrow pushing. Deprotonate here. And I'll draw the enolate where I leave the lone pair on the carbon atom. And that way it's easier for you to see where's the nucleophilic part of an enolate. Now, you might be wondering, well, wait a second, doesn't the alkoxide attack the carbonyl? Yes, it does, but that's not, it doesn't lead you anywhere. So if you're frustrated by that, let me just kind of in the side in a completely different color say, yeah, there is some reaction where the alkoxide is attacking the carbonyl. But that can do absolutely nothing except go back. It's happening. But don't worry about that. Who cares? Who cares that the alkoxide is spending some time attacking the carbonyl, because it's just going to push the alkoxide right back out. So don't worry about that. What matters is that we're making small amounts of enolate, and enolates are nucleophiles. So as soon as this enolate here runs into another carbonyl compound, another aldehyde. Well, let me change that to red here. It's going to form a carbon-carbon bond, and that's really the exciting part of this chemistry. Now, already in this step, I've created two new stereogenic centers. Man, so just for now, ignore the stereochemistry and let's just focus on this new carbon-carbon bond that we made. That's awesome. And in step one, I generated this protonated base. I could have written HB just for the arrow pushing. And it's just going to pull a proton off of our base like that. And there we go. And that's the mechanism for the aldol reaction. It's a 3-step mechanism, and it's super important. And this is really starting with malonic ester derivatives. It's this kind of chemistry that generates carbon-carbon bonds. And well, we'll get there in the human body. Okay, this is a super important reaction in organic synthesis, and it's also super important in organisms that produce a class of natural products called polyketides. Plants and lower organisms produce polyketides using aldol type chemistry. And when you look at the structures of some of these compounds, some of the most potent medicines and potent molecules that we know about in terms of biological activity are best made using aldol reactions. So here's an example of a natural product that was discovered by natural products chemists. Their job is to just fly around the world or take boats around and dive deep into the ocean and collect sponges. Because here's an example that has 2 different names, probably discovered by 2 different groups, called spongistatin. It's produced by a sea sponge. You know, a sea sponge is delicious to sea organisms, so they need some way to protect themselves. So they produce some of the most potent compounds known for killing cells. If you want to stay alive and you're a sponge, you better have your game on with chemical warfare. So here's an example of one of the most potent compounds known for killing cells. And if you're trying to kill cancer cells, this is the stuff. It's active. I mean, do I even have it here? I think it's active at 20 picomolar. I don't like, what is pico? I don't even know. It's like nano and then pico. That's the concentration at which half the cancer cells will die. It's like that amount is so vanishingly small. And we can't design things like this just from scratch using benzene rings and electrophilic and aromatic substitution. And you can't dive into the ocean and collect enough sponges to treat patients with this compound. The only way you're going to get molecules like this in quantities that are large enough to treat people is using total synthesis. So synthetic chemists go after these. They try to figure out how could we make that. If we can't get enough from collecting sea sponges, how would we make this in the laboratory? And the way you do this is you look at the molecule, this class of molecules called polyketides, and you can see, if you understand the aldol reaction, everywhere you see this pattern of a hydroxy group 3 carbons away from carbonyl, you could have made one of those bonds through an aldol reaction. And if you know about a sodium borohydride reduction like this, you know that anytime you see 2 hydroxy groups 3 carbons away, that could have come from doing a hydride reduction after an aldol reaction. And if you know how to do Wittig reactions, that means anywhere time you see a molecule that has this pattern in there, that could have come from an aldol reaction followed by a Wittig reaction. Or if you do an elimination reaction here to make an alkene, well, that could be derived from doing a Wittig reaction followed by a dehydration event. And so the synthetic chemists, this has been made by more than one synthetic group. Here's one example of how they did a retrosynthetic analysis to figure out how are we going to build this molecule. And you can see how many times they used aldol reactions in the construction of this. They said, okay, I see a carbon atom that's 3 atoms away from another one substituted with oxygen. This ketal could have been derived from a carbonyl group. So, they looked at this and said, this could have been derived from an aldol reaction. Here's a carbon with an oxygen on it that's 3 atoms away from what used to be an aldehyde before it got converted to a ketal. Here's another thing where there's a pattern with oxygen next to something that could have been generated to a Wittig reaction. All these different bond disconnections were, they analyzed and said, I could build that bond through an aldol reaction. And that's exactly how they synthesized this molecule. We did a bunch of aldol reactions and then Wittig reactions and hydride reductions, and were able to assemble close to the world supply of this molecule. Okay, but we're doing it on simpler substrates. You don't have to analyze targets that fancy. But I do expect you to know these patterns of reactivity. So There's a simple extension of the Aldol reaction called the Aldol condensation. And the word condensation means you're eliminating out water. You're getting off water from the reaction. Okay, so here's an example of what's going on with an aldol condensation. So when you do an aldol, of course, aldol reactions involve two molecules coming together. One enolate attacks another carbonyl. So I'll draw the two molecules, although that shouldn't really be necessary for you. And the initial product that you get in this reaction is the product of an aldol reaction. But because they're heating it, because they're heating that reaction, it can go further. You don't isolate this under these conditions where you're heating it. This will undergo further elimination. So we don't usually draw. I don't usually draw these H's. There's an H here, and so that means you're generating as a byproduct H and OH. So water is the byproduct. We usually only draw the organic products in reactions. We don't draw the salts you get. Nobody isolates the salts. We isolate the organic products. And this process of doing an aldol and having it spontaneously eliminate under the conditions of the reaction is called an aldol condensation. Now, it's possible to get E and Z isomers here, so I want you to recognize that. I only drew the E isomer here, but you also get a little bit of the Z isomer. And I'm telling you, I expect you to recognize any reactions where you generate stereoisomers, either R and S or either E and Z. I'm going to write over here plus Z, just to indicate that we recognize that you get some of the Z isomer. Okay, what's the mechanism for this elimination reaction? Now, going back in time in our course, you've spent maybe 8 months, I don't know, learning E1 reactions and E2 reactions. And that's not the most common elimination mechanism. I'm going to show you the most common elimination mechanism in organic chemistry, and it's not E1 and it's not E2. The most common elimination mechanism in organic chemistry is that you deprotonate next to carbonyls to make enolates or stabilized carbanions. So this first process here is to make some sort of an enolate. And this is what's happening in the aldol condensation. And once you have a carbanion next to a hydroxy group, the hydroxide easily acts as a leaving group. Now, I know you were taught some rule that says hydroxide never acts as a leaving group in SN2 reactions. This is not an SN2 reaction. Hydroxide easily acts as a leaving group. Let me just remind you that we've seen these kinds of intermediates before, like when we did Grignard additions. If you did Grignard additions to make species like this, it was pretty common for us to see alkoxide to act as leaving groups when you did things like Grignard addition. So there's nothing new about anionic lone pairs pushing out alkoxide or alkoxide leaving groups. So now we're using an enolate carbon to push out an alkoxide or hydroxide leaving group. That's not special. I'm going to tell you, don't draw this concerted, and then you're going to forget, and you're going to try to draw this mechanism out as a concerted E2 elimination. It's not concerted. That's wrong. That's wrong. Let me just write wrong. And then I'm going to remind you that, well, I told you were going to forget. And why do I know you're going to forget? Because you've had months and months to learn E2 eliminations, and remember that. And you've only had 1 day or 1 hour or 1 minute here to learn about the E1CB elimination mechanism. Make a stabilized carbanion and then push out the leaving group. It's 2 steps. It's not 1 step. Okay, so this process of aldol condensation or aldol or a simple aldol reaction is pretty powerful. So how would you know whether it's going to stop before it does the elimination of water? And the book is never clear about that. It's so frustrating to me. So I'm going to give you a simple rule that tells you how do you know whether it's going to eliminate for sure. I'll give you 2 rules. First of all, if heat is added as one of the reactants, then you should assume it's going to eliminate the water, the H, the beta hydroxy group. So if I write sodium hydroxide, it doesn't stop at the aldol reaction if I write heat as one of the products. You should simply assume it's going to lose water out of that process. So there used to be an H and an OH where the alkene is. But if I just simply write sodium hydroxide with no heat, then there's no reason for you to assume it should eliminate. You should assume it's going to stop at this beta hydroxy compound without eliminating the H and the OH. Again, there's an H over here that I'm not drawing, right? That's getting eliminated. So heat is one indicator that you should get in elimination. There is a rule the book gives you about when to know that it's going to eliminate um, and give you an aldol condensation. And the rule is that if the new CC bond can be formed with conjugation, then you don't even need the heat. Let me give you an example of that. So I'll go ahead and draw it as a starting material, this time a ketone. And if I drew another molecule, let me try to arrange it here so you can see where the pieces are going to go. So if I had two of those molecules, you can kind of tell that it's possible to form a bond, a double bond between these two atoms. Make an enolate, have it attack the carbonyl, and make a CC double bond. And let me get rid of that highlighting there. So in this particular case, let me go ahead and draw out the benzene rings here. And so maybe it's not, maybe it should be obvious, but yes, you can do aldol reactions with ketones instead of aldehydes. You just need to be able to make an enolate. And how would you have known that this doesn't require heat? How would you have known that it's going to spontaneously eliminate? Well, if the product can be conjugated, and let me be very clear where the conjugation has to be. So if this double bond and this carbonyl are conjugated on this side, forget the other side, on this side over here, then it's going to spontaneously eliminate. It doesn't matter that there was a benzene ring on the left-hand side of the molecule. So you get this extended conjugation, which is highly favorable, and it's hard to stop those from eliminating. So even without heat, if you can get this kind of conjugation to make a dienone, the substrate could have had a simple double bond there, then those spontaneously eliminate even without heat. Okay, so two different cases in which you're going to get elimination. One is heating it. In my class, when I say heat, you should assume it's going to eliminate. And then the second case, as the book says, is if you can get this kind of conjugation to make a dienone, where the new double bond is conjugated to either a benzene ring or just an alkene, those will also do the spontaneous elimination. All right, you know, I'm not sure if this is obvious, but you have to have alpha hydrogens in order to make enolates and in order to do aldol reactions. So if you take a substrate like benzaldehyde, you'll notice here's what would be required for an aldol reaction. You have to have the capacity to make enolates. So a molecule like this has a carbon atom with a whoops, wow, what was that? I've never seen that function before. Well, let me go backwards. A molecule like this has an alpha carbon and a hydrogen atom attached. You can make an enolate out of that, but you can't make an enolate out of this. There isn't even a carbon atom there. You can't make and over here on this carbon, there's no H's on it. You can't, I'll just say no enolate. Let me just write that down. I'm not saying there's no reaction. There's a secret reaction. That's just poorly drawn. No enolate. You can't make an enolate out of benzaldehyde. It does an odd reaction that we're not going to talk about called the Cannizzaro reaction. You don't need to know that. But you're not going to make any enolates out of benzaldehyde. Forget that. There's no way. And let me just once again remind you that ketones can undergo aldol reactions. Ketones are less reactive in general. Aldehydes are way more reactive than ketones, maybe 1,000 times more reactive. So you can do aldol reactions with ketones. They're just not as fast as adding to an aldehyde. So I'm showing you this here. That's you have to recognize this pattern. If I show you this molecule, I hope all the class would say, "Oh yeah, I could have made that through an aldol condensation." Whenever you see enones, you should be thinking, "Gee, I think I could have made that out of an aldol condensation." And so you can do that with ketones as well as aldehydes. So I expect you to do that. So this idea of doing retrosynthetic analysis on the exams, we're going to have multi-step syntheses where it's like, here's a product, how would you make it from these starting materials? If I show you this product here and I say, how would you make that? I fully expect you to have practiced enough problems in the book enough problems in sapling where you can easily see that you could have made that out of cyclohexanone. Here we go. These are the conditions for that reaction. You just take cyclohexanone and sodium hydroxide. If you want, I'll draw the second molecule of starting material, but you shouldn't really draw a second molecule if we're just drawing out reaction conditions. So you should be able to see in your mind that you could have made that through an aldol condensation. Here's another example that's a lot trickier. So the second example here, I see an enone, and I hope you're thinking, well, I could make that through an aldol reaction, and you're going to have to practice this to see what's going on. So here's the bond. Over here is the bond that could have been made through the aldol reaction, where you make an enolate here and it detects a carbonyl right here. So let's go ahead and draw that substrate out. I'll just draw the benzene ring out as a phenyl. So I should have, let's see, 1, 2, 3 atoms. The 1, 2, 3 atoms, then a carbonyl group. And then there's this methyl group sticking on the top. And there needs to be a carbonyl group right here. There we go. And that would be the recipe for, I think I got this weird looking dot here, so I'll try to erase that. And that's the recipe for an aldol reaction. If you took that substrate and treated it with sodium hydroxide, you'd get an aldol addition and a condensation, elimination of water. How would I know that I don't need to heat it? Well, that's because it's got this conjugated enone system here that you should be able to see. It's not wrong if you put heat as an ingredient for the reaction, but you don't need heat for that to eliminate. It's going to eliminate spontaneously. Here's an example of a molecule that you should be able to make. And maybe it's easier to see that that these two pieces have like a similar substitution pattern if I point the ethyl group down. This is the same molecule. So I hope you can see that you could have made this doing an aldol addition reaction. All we need is sodium hydroxide and then the correct aldehyde here. That's the aldehyde. It's got an ethyl group. So if I take butanal and I add sodium hydroxide to that, I should get this product, this aldol addition product. And as long as I don't put heat as an ingredient, it won't give me the elimination. So the aldol reaction, you have to practice it. You have to work lots of problems to be able to see when you're looking at a product how that could have been made through an aldol reaction. And practice enough times where you really know how to do that. All right. Let's go ahead and talk about one. You know what? I think I'm going to stop right there. I'm going to stop right here on crossed aldol reactions. That's taking ketones and aldehydes and getting one to form the enolate and the other one to get attacked. And let's just go ahead and wait until we come back on Friday to do that. And for now, you need to start practicing making enolates and having them add to carbonyl groups. We're going to make enolates and have them add to aldehydes. We're going to make enolates and have them add to ketones. We're going to have enolates and have them add to esters. We're going to make enolates and have them add to enones, just like a cuprate does. That's really the culmination, mostly, of chemistry 51, is making enolates and having them add to carbonyl. It's bringing us really close to modern organic chemistry. All right, I will see you guys on Friday, and stay safe and keep working lots of problems.